On the previous video, we applied the method of separation of variables in solving for the solutions to first-order differential equations. But how about if the given first-order differential equation is not yet variable separable? So in this video, we will introduce another method of solving the solutions to first-order differential equations. Uh, and this and this method can only be applied if the equation is homogeneous differential equations. And these equations are said to be homogeneous if the coefficients m and n are of the same degree. And the formal definition of homogeneity is the function is said to be homogeneous of degree k in x and y if and only if. So we have this equation, uh, the function multiplied by lambda should be equal to lambda raised to k times the function. So basically, to test the homogeneity of the equation, so we just have to multiply the function by, we just have to multiply x and y present on the equation by lambda. Then after that, we apply some techniques in algebra to factor out the lambda. The resulting exponent of the lambda will be the degree of differential equation. But how about if we cannot factor out the lambda present on the differential equation? So, if we cannot factor it out, uh, the differential equation is not a homogeneous differential equation. So let's now try to identify these following equations, whether it is homogeneous or not. So let's test their homogeneity. So we have determined whether the following function is homogeneous or not and state its degree. So first function is function of s and t is equals to 2s squared plus 2st plus t squared. So we just have to follow this statement. So we have, first is we will multiply uh, each variable by lambda. So we have the function of lambda s and lambda t is equals to, so we have 2 times, since we have this s squared, we will multiply it by lambda squared plus 2 lambda s lambda t plus lambda squared t squared. Then after that, we factor out the lambda present on the function. So we just arrive with this form, lambda raised to k times the function. So k will, the value of k here is 2. So that's why we have this homogeneous differential equation is second degree. So next will be, we have the function of x and y is equals to x tangent of x over y plus y. So again, we multiply the variables on the function by lambda, so it will be equal to lambda of function of lambda x lambda y equals to x multiplied by lambda. Then for the angle, we have lambda x over lambda y plus y, I mean lambda y. So for the angle, so lambda here will just be cancelled out. So what we will only be factored here is lambda. So we have lambda times x tangent x over y plus y. So since we factored out the lambda on the function, so it will be, this function is a homogeneous differential equation. And the degree of this homogeneous differential equation is first degree. So next would be, the function of x and y is equals to tangent of x. So again, we multiply the function by lambda, so it will be tangent lambda x. And since x here is an angle of the tangent function, so we cannot factor out lambda here because it belongs to the angle side. So therefore, it will be, this function is not a homogeneous differential equation. So for number 4, we have function of x and y is equals to x raised to 3 minus xy plus y cubed. So again, we multiplied the function or the variable present on the function by lambda. So it will be lambda raised to 3 times x cubed minus lambda x times lambda y plus lambda raised to 3 times y cubed. So we can only factor here is lambda squared, since the common factor here is only lambda squared. So there is still a remaining lambda inside the function. So that's why this differential equation is not homogeneous. Then for number 5, we have the function of x and y is equals to, we have x squared plus y squared times the exponent raised to, or I mean e raised to 2x over y plus 4xy. So again, so we multiply each variable by lambda. So we have lambda squared x squared plus lambda squared y squared e raised to 2 lambda x over lambda y plus 4 lambda x lambda y. So the lambda here will cancel out. So 2 lambda x over lambda y will just be 2x over y. Then we factor out lambda squared. So since we factored out the lambda present on the function, so therefore this function or this differential equation is a homogeneous differential equation. And then the degree of this differential equation is second degree. We are done identifying whether the differential equation is homogeneous or not. So let's now proceed on the solution steps on how to solve this kind of differential equation. So here are the solution steps. So take note first that we have to rewrite the given equation into into its standard form. So the standard form of a first order differential equation is m as a function of x or y dx plus n as a function of x or y dy dy, as a function of x or y dy equals to 0. So our objective here is to reduce the equation into variable separable form. That's why I mentioned earlier that what if the equation is not yet variable separable. So we just have to find a way first to make the given equation into variable separable. So here are the steps. We first step is replace y by ux or x by vy. So we will be deciding whether we use y or x to be substituted. So in deciding, so we just have to decide uh, which of the coefficients is simpler. So if n is simpler, we have to use y. So if y is equals to ux, then we take the derivative of this y is equals to ux. So it will be dy equals to u dx plus x du. So we apply the product rule. So, and if m is simpler, so we use x. So substituted by vy. Then we take the derivative. So dx is equals to v dy plus y du. I mean y dv. Again, we apply the product rule. Then after we decide which is simpler, and after we also substituted the coefficients, so we have to simplify the resulting equation. Then after simplifying, we have to separate the variables. So meaning, so the given equation is not yet variable separable. Then after replacing the equation by y by ux or vy, so it will make the equation variable separable. Then after the equation becomes variable separable, so we can now integrate the equation to get the general solution. Then after solving for the general equation, we substitute it back to its original variable, x or y. So to obtain the general solution in terms of x and y. So let's try to apply the solution steps on how to solve a homogeneous differential equation. So let's consider this example. So we have obtained the general solution of the equation x minus 2y multiplied by dx plus 2x plus y multiplied by dy equals to 0. Then the first step is we have to reduce the given equation on its standard form, and just by looking at it, this equation is already on its standard form. So next step is we decide which of the coefficient is simpler. So in this case, m and n are both simple, so we can just pick any of the coefficient. So let's say we choose m to be simpler. So if we choose m, so we let x to be vy, then dx to be v dy plus y dv. Then after that, we substitute x and dx on the equation number 1. So the result will be, so your x becomes vy, then dx becomes v dy plus y dv. So x here also becomes vy. Then after that, we simplify the resulting equation. So in this case, we just have to apply the FOIL method on this side, and this side we just have to distribute dy. So the result will be v squared y dy minus 2vy dy plus 2vy dy plus y dy plus vy squared dv minus 2y squared dv. Then after that, so for this equation, so 2 by dy will cancel out since we have 2 by dy plus 2 by dy. Then we factor out y dy on these two terms. Then for these two terms, we have to factor out y squared dv. So it becomes, so we factor out y dy, so the result will be v squared plus 1 times y dy. And so on this side, we factor out y squared dv, so it becomes v minus 2 multiplied by y squared dv, then equals to 0. So as you can notice, this equation becomes variable separable. So let's now separate the variables. So it becomes y dy over y squared plus v minus 2 dv over v squared plus 1 equals to 0. Then after that, we can now apply, or we can now integrate the equation. So it will be, so y dy over y squared, so we cancel out y, so it becomes dy over y. Then we take this each antiderivative. So minus this v minus 2 dv over v squared plus 1. So we separate v and negative 2. So it becomes negative 2 the integral of dv over v squared plus 1 plus v here, v dv over v squared plus 1 equals to 0. So to integrate dy over y, so we just have to apply the formula for integration, du over u. So the integral of du over u is equals to ln of u plus c. Then for this expression, so we have to use the inverse trigonometric formula. So we have the integral of du over u squared plus 1 is arctangent of u plus c. Then for this expression, the integral of v dv over v squared plus 1, we can just apply the u substitution. So we let u equals to v squared plus 1, then du is 2 2v dv. Then we substitute your u is v squared plus 1, let's divide both sides first by 2. So du is 1/2 du is equals to v dv. Then after that, we can now substitute u and du. So the integral of v dv over v squared plus 1, so v dv is 1/2 du and your u is v squared plus 1. So we have 1/2 integral of du over u. So that integral of du over u is ln of u. Then we substitute u by v. So your u becomes v squared plus 1 plus c. So let's combine all the terms. So we have the integral of dy over y is ln of y. Then the integral of negative 2 dv over v squared plus 1 is negative 2 arctangent of v, plus the integral of v dv over v squared plus 1 is 1/2 ln of v squared plus 1 equals to c. So after we arrive with the general solution in terms of v and y, we have to return it back in terms of x and y. So we substitute u is equals to y over x, or v is equals to x over y. So in this case, we have to substitute it back to x over y for v. So it will be ln of y minus 2 arctangent. So your v is x over y plus 1 half ln of v squared is x over y squared plus 1 equals to c. Then let's try to simplify this equation. So to simplify this equation, first is we have to multiply both sides by 2. So to eliminate this fraction. Then after that, since we have a logarithmic expression, so we can apply rules in logarithm on 2 ln of y plus ln of the square of x over y plus 1. So this becomes, so we have ln, so y squared times x squared over y squared plus 1 minus arctangent of x over y equals to c. So we multiply these two terms, so y squared times x over y squared, so we cancel out y squared. So it becomes, we have ln of x squared plus y squared. So we multiply y squared by the square of x over y, then y squared times 1 is y squared. Minus arctangent of x over y is equal to 0. Then, so that will be the final answer. So let's proceed with the next example. Obtain a family of solutions from the equation x squared plus y squared multiplied by dx minus xy multiplied by dy equals to 0. So first step is we have to reduce the equation to its standard form, and this equation is already in standard form. So after that, we decide which of the coefficient is simpler. So in this case, we choose n to be simpler. We have xy is much simpler than x squared plus y squared. So then, if we choose n to be simpler, so we have to substitute y by ux and dy by udx plus x du. So let's now do this. So we have the resulting equation will be x squared plus your y is ux squared dx minus x times y is ux, then dy is udx plus x du. So after that, we simplify the equation. So for this equation, so we have to factor out x squared dx. And also, if we distribute this one, so x times ux udx, it becomes x squared u squared dx. So some terms will cancel out here. So the resulting equation will be, we factor out x squared dx, so it will be u squared plus 1 minus x times ux udx is x squared u squared dx minus x ux times x du is x cube u du equals to 0. So then we factor out again x squared dx, so it will be u squared minus u squared plus 1 minus x cubed u du equals to 0. So u squared will cancel out. So the resulting equation will be x squared dx minus x cubed u du equals to 0. So in this case, this equation is already variable separable. So let's now separate the variables. So it will be, so from the equation, so x squared over x cubed becomes 1 over x. So that's why we have dx over x here. Then also for, so what will remain on the du side is u du only. So that's why we have u du equals to 0. Then we integrate the equation. So we have the integral of dx over x plus the integral of u du is equals to 0. So the integral of dx over x is ln of x, while the integral of u du, so we have to apply the power rule. So it is u squared over 2 equals to 0. Then we can now substitute u back to y. So we have ln of x minus your u is y over x squared over 2 equals to c. Then we multiply both sides by, we factor out, we transpose this term, the square of y over x over 2 on the right side of the equation. Then we transpose also c on the left side. So it will be ln of x minus ln of c equals to y squared over 2x squared. So we already simplified this term. The square of y over x is y squared over x squared. Then after that, so we combine these terms. So it becomes ln of x over c by applying some rules in logarithm equals to y squared over 2x squared. Then, so we cross multiply 2x squared. So the resulting general solution will be 2x squared ln of x over c is equals to y squared. So that will be the final answer. So next example would be obtain a family of solutions from the equation y squared dy equals to x multiplied by x dy minus y dx multiplied by e raised to x over y. So first step is we have to reduce this equation to its standard form. So to reduce it to its standard form, we have to apply some algebra rules. So we have to distribute these terms. So we have x times x is x squared times e raised to x over y dy minus x times y is xy times e raised to x over y times dx. And then we transpose all these terms on the left side of the equation. Then we factor out dy. So the result will be xy e raised to x over y dx. Then we have y squared minus x squared e raised to xy multiplied by dy equals to 0. So this will be the standard form of this first order homogeneous differential equation. So next is, so we decide which of the function of x and y is simpler. So obviously m will be simpler than n. So if we choose m, we have to replace x by vy and dx by vdy plus y dv. So and then, so let's now substitute x and y on equation 1. So the result will be your x is vy then your dx is b dy plus y dv. So plus y squared minus b, your x is by raised to 2. E raised to your x over y becomes by over y times dy equals to 0. Then after that, we distribute these terms. So the result will be, so by times y e raised to by over y times b dy plus y dv. So the result is b squared. So we have v times v is v squared, y times y is y squared, e raised to, so we cancel out y, so we have e raised to v times dy plus y dv times by times y is y by cubed, e raised to v dv plus y squared times dy is y squared dy, negative the square of vy, e raised to v y over y, so the result is v squared times y squared e raised to v times dy. So next would be, so v squared y squared e raised to v dy minus b squared y squared e raised to v dy, so it will just cancel out. So what will remain is by cubed e raised to v dv plus y squared dy is equals to 0. So this equation is now variable separable. So to separate this variable, so we have to divide both side, or I mean we have to multiply both side by y cube. So the equation becomes, so y cube time, I mean we have to multiply both side of the equation by 1 over y cube. So the resulting equation will be ve raised to v dv plus, so 1 over y cube times y squared is y na lang. So we have dy over y equals to 0. Then we can now apply integration. So we integrate, so we have the integral of v dv, I mean v e raised to v dv plus the integral of dy over y is equals to 0. So let's now integrate. So we have to, let's integrate this side first. So the integral of dy over y is ln of y plus c. And to integrate this expression, integral of v e raised to v dv, so we apply integration by parts. So we let, anyways, the formula for the integration by parts is the integral of, so instead of v, I use z since we have v present on this expression. So the integral of udc is equals to uc minus the integral of c du. So we let u as v, and we integrate u, so we have du is equals to dv, and we let dc as e raised to v dv. Then if we integrate dc, so we have z is equals to, so we apply the integration of logarithm. So the integral of e raised to v dv is e raised to v plus c. So then we now substitute u and u du and dcz to our formula. So we have the integral of udc is, u is v, then du is e raised to v dv, u is v, z is e raised to v, minus the integral of z is e raised to v, then we have du is dv. So we have the integral of e raised to v dv is e raised to v. So this will be the result after applying integration by parts. So we factor out e raised to v, so the result will be e raised to v times v minus 1 plus c. So let's combine all the terms. So we have e raised to v times v minus 1 plus ln of y equals to z. So that would be the general solution expressed in terms of v and y. But we have to return it back to its original variable, which is x and y. So we have to substitute v by x over y. So e raised to v times v minus 1 plus ln of y is equals to c. So your v is x over y. So we have e raised to x over y times v x over y minus 1 plus ln of y equals to c. So then we transpose c on the left side, then e raised to x over y times x over y minus 1 should be transposed on the right side of the equation. So the result would be ln of y, then c, make it ln of c. So ln of y minus ln of c equals to e raised to x over y. So since after transposing, this expression becomes negative, then we distribute the negative sign so that it becomes 1 over x over y. So ln of y minus ln of c is ln of y over c equals to x over y. Then we multiply both sides by y. So we have y on the left side, y ln of y over c equals to e raised to x over y. Then y times 1 is y times over x over y is x. So this will be the general solution of the homogeneous differential equation.